Go. My turn. Is that right?
You're up. You're up.
Very good. All right, gentlemen. Sorry for the mix-up on password. Our blame system is still searching for where the problem came from. But the recovery was absolutely spectacular because we have 26 people online uh, having received the wrong password. Um, and I was in an online with the Zoom support people, and fairly quickly they gave me a solution, but the solution was worse than the disease. So we put out the new password, and I was able to get it onto the 3 Facebook pages immediately, and we recovered some of our international people. So the topic today for our challenge is to program the game in Northern California. It's called Roshambo, and I understand that's a regional naming for the game of rock, papers, and scissors. So do we have any people who have programmed rock, papers, and scissors who would like to present? Jürgen, is there a hand up? I think I see the hand up, so it must be.
Dave Henderson.
And Brad. And Peter. Very good response. All right, we have Jürgen, we have Brad Nelson, and we have Peter. Anyone else?
Sorry, I don't know why I'm on. Definitely not. That's too high for me.
Oh, so that's a no from Jürgen?
Yes.
Okay, very good. So we have Brad Nelson and we have Peter. Is that correct? No? Oh, okay. Do we have Brad Nelson aboard for rock, paper, scissors?
After fashion, yes.
All right.
You also have Dave Henderson.
Let me jot that down.
In the chat, he's saying he can present.
Ah, excellent. So we have Brad Nelson and Dave Henderson, and I'll bat cleanup. All right, Brad, please take it away. You're muted right now.
Unmute myself. All right. So rock, paper, scissors. So I thought I'd use micro E4 this time, and that was sort of what I gave a go to. This one was a puzzling one, Bill, and I'll be curious to see what you present with it. I didn't do as much as I might have otherwise. One thing I ran into actually, I found myself running in circles with my random number generator, and playing around with random numbers gets you paranoid if you discover you've got a bad one. So I finally resorted to like, well, I'll just use dev urandom, the cryptographically random file source on Linux to pull out some bytes for random number generation. What it turned out, this actually helped me uncover a bug in micro E4. I discovered that in some of my fiddling around with */mod, actually, I had accidentally broken my flooring mod such that it didn't do the correct thing for negative numbers in one case that I inadvertently relied upon. So little housekeeping, I needed to be able to tab and a way to print a word easily in micro E4. And then based on that, what I did was I came up with the notion of a creating word called thing that lets me create a thing for a rock, a paper, and a scissors. It assigns each of them a reference to their dictionary entry, but also an ascending ID. So, rock, paper, and scissors are 0, 1, 2. And then I've got a word play that you can take two things and have them compete, and it'll return a 1, a 0, or a -1, depending on whether the one on the left or the right one. And this is more bookkeeping and just a way to evaluate a single word. And then for interactive play, I've got a word that goes and prints out a command and then parses from the user. And let me go ahead and show this. So for interactive play, it's just, I gotta run my, so I'll do include scissors. And so a round of rock, paper, scissors, if I do rock and I do paper, and then you can hit enter to reveal, and player B wins. So that's for interactive play. I then wanted to have a mode of operation where there's autonomous players. So I've got a notion of a player as an execution token to describe what they do. They do a spin and then they take a thing. And so for a round of competition, you'd have two of them where you take an execution token for each and have them play against each other. And then I've got a word rounds that does multiple rounds, taking two players and then some number of rounds and then computing their aggregate score. That word looks strange. There appears to be a cut and paste error in the slides that disregard that first word. What is going on there? Oh, I think this is a glitch with my slide thing. Okay. I'm puzzled by that. But anyways, okay. That's a bug I will be addressing separately. That R should be an R greater than. So then I've got a word player that specifies a definition for a player that lets them be defined in terms of their relative weighting for rock, paper, and scissors. And so you can have a 50, 25, 25 split or a 1-to-1 split for Betty and Alan. And so, for example, then you could have Alan and Betty, and you could have them that they can go at it for 5 rounds, and they compute their into the individual rounds, and then an outcome, and then an aggregate score, and it's random, so very likely it will be different if we do 5 more rounds. And this time it went the other way. But of course that's verbose if you're going to do lots of them. So there's some conditionals in there around verbosity. So I can turn off the verbosity and have Alan and Betty go at it for 100,000 rounds, and they'll tick away. And out of that many rounds, things stayed in the middle. And so the net result seems to be that for at least a purely random autonomous entity, you get something approximating a break even, regardless of the strategy used. My sense is that this is there's all kinds of things that you could do if you had statefulness and you had the assumption that one of the other entities was sort of trying to communicate with you through successive rounds. Was thought about exploring that, but distracted with other things, and so this is as far as I got. Are there any questions?
That looks very good. It warms my heart when we talk about Alan and Betty. I think that's nice to personify the game. It's much better than having player 1 and player 2. Any final questions here? Come up now.
I will say my experience chasing my own tail with a random number generator reminded me of a story I actually heard once from some Russian plasma simulation folks who they had what they thought was a great discovery in physics, and only to learn that they just had a bad random number generator. And so I had a relatively similar experience last night. So.
Personally, I have a preference for Alice and Bob, like in Bruce Schneier's books, but that's personal.
Indeed. Although now I'm imagining what Mallory does to subvert the game.
Great, Brad. Thanks so much. And next up is Dave Henderson. Take it away.
Okay, can you hear me?
Perfectly, yes.
Oh, perfect. Okay, I'll start with, I'll share my screen first. Okay, here's the code. Can you see my code here? Anyone?
Yes, we can see your code.
Okay, thank you. Okay, so the first challenge, level 1, was to do rock, paper, scissors, make it be able to play the game interactively. So I defined some constants for rock, paper, scissors, and it made something to print the hand that you're dealt, and then print the outcome from applying those hands, and a comparison for them. If the opponent wins and 0 if a tie. And then I print the round, pretty simple, and say which one wins at player A or player B. And wrote some test code here, like a good engineer should do, I guess. And tested the outcome here, and here you can interactively put in rock, paper, scissors for the first and second player and print the round. Level 2 was to create a learning strategy for Betty. Again, I had to find a random number generator, so I found something from Wikipedia, and I think it's Microsoft Basic random generator algorithm, and it's pretty simple. And anyway, I use a seed, which starts the same every time, so I can kind of see whether it's predictable in that way. And here's the algorithm I use for it here. And then I make a move for Alan, which uses the poor random generator, number generator, and I get 0 through 3, and I map 3 to over to rock, so I get a 50% chance there. Betty, I just have her pick 0, 1, or 2, which is rock, paper, scissors. And then the algorithm to test it out, I do 100,000 loops. I'll make Alan's move, Betty's move, compare the hands, and tally up the counts for Betty and Alan, and show their number of wins and the number of ties. And as far as the challenge to find what the best strategy was, I determined, I think, that the strategy is that Betty always picks paper. And then I copied and pasted here to use Betty's better strategy and get wins, ties, and for Betty and Alan, and ran it in VFX Fourth. Hopefully you can see my screen here. Here's my kind of test table to test out all the outcomes to make sure I had my logic right. And then down here I did Betty picking randomly rock, paper, scissors against Alan's strategy, and I got about a third, which I hope is correct. And then with strategy of Betty always picking paper, I ended up getting Betty wins 50% of the time. And that's it. Thank you very much. If you have any questions, let me know.
I'll make a point here, which we may get to later, but you see, since there are randomness in the picks, there still will be ties. And theoretically, the ties should always stay at about 1/3. And Betty's wins go up and Alan's goes down, but the ties still come to haunt. Any further questions?
Just lost your sound, Bill.
Yeah, you're muted.
Got it. Good. Very good. We're back in business now.
we've got no sound.
I don't have any sound.
Up. Up. Good. Thank you for the reminder. Little cockpit trouble, but we will fix it.
Tell you what, how about we go rock, paper, scissors? Ew, I don't think so. No, anecdotal evidence suggests that in a game of rock, paper, scissors, players familiar with each other will tie 75 to 80% of the time due to the limited number of outcomes. I suggest rock, paper, scissors, lizard, Spock. What? It's very simple. Look, scissors cuts paper, paper covers rock. Rock crushes lizard, lizard poisons Spock. Spock smashes scissors, scissors decapitates lizard, lizard eats paper, paper disproves Spock, Spock vaporizes rock, and as it always has, rock crushes scissors.
Thank you, with credit to Dave Jaffe for locating our introduction piece. So, to summarize, I forgot to mention at the very beginning that with rock, paper, scissors, it's essentially a tie game unless one player has an advantage or the other one has a deficiency. And we specified in this that Alan would pick rock 50% of the time. So to start to program the game, we then engage in systematic testing, and then the final phase is strategy development. As we all probably know, the 3 players alternate. This is our definition of the game. They play the 3 tokens, rock, paper, scissors, and it's each can win, lose, or draw. So therefore, this is a zero-sum game, and that's all I know about game theory, except for the fact that a naive strategy should just be to mimic your opponent. And the trade-offs are that rock breaks scissors, scissors cuts paper, paper wraps rock. So if we create a matrix, an XY matrix, we're going to say that Alan's plays will go along column, Betsy's plays will go along a row, and then at each intersection, there will be an integer, which gives the result of the game. So at the top left, we see for Alan's with a rock, and at the right, Betty with a rock. The intersection is a tie, which gives us a 0. And looking at the diagonals, paper against paper and scissors against scissors also give a tie. However, going back to rock at the top left, the second row down, Betty plays paper, you get a lose, and you get an integer of 3. So each integer tells us is coded to give us which player won and why. So here's the pseudocode. It's along the line of what we've already seen. We create the logic. We have to have report elements. We have the play process. We have a reporting process. Then we go to automatic play, and then we analyze the results. So here in 4th form is an array named outcome. We create the array, and then we comma into it those 9 values that correlate to the outcomes. We'll give each element a value. Rock has a value of 0, paper has a constant value of 1, and scissors is a value of 2. To play a game is simple. We have a result selection. We show the result. We show the reason for the result. Now to look up into that outcome matrix, result selection does a row column adjustment, goes to the particular outcome element, does a C fetch. This gets us our result of the game, and then the game result is analyzed. The second from the bottom row is an actual game. Alan plays paper, Betty plays rock, and then a game goes to the outcome. And then at the bottom row, we see the report that we get, which says Alan wins because paper wraps rock. This is the decision process. The 2 values go, or the value from that decision matrix is read by log game result into result, and then an increment is made to the number of ties. Did Betty win or did Alan win? So the word ties and Alan are there, and Betty are their win-loss results. And so we see the case of 0 means there's been a tie. Alan wins in the case of 1, 4, and 5. Betty wins in the case of 2, 3, and 6. To show the result, again, from that game result integer, 0 is a tie. Alan is for a 1, 4, and 5. We get a report of Alan winning. 2, 3, and 6, Betty wins. The reason for the win, again, the 0 is silent because we already know that it's a tie game. There is no reason. Then again, 1 through 6 now shows why the win occurred. For example, in number 1, paper wraps rock. And again, there are 6 cases of win-loss and then 1 case of tie. So for strategy development, the key point here is that your opponent must have a bias or you must have an edge. If the games are truly at random, it'll always be ties. And as we saw in that video, though, people often inherently have some sort of a preference or a bias, and often opponents can figure it out. So in strategy development, if you win, the idea is do more of it. If you lose, do less of it. This is not PhD material at this point. A smaller point is that you should vary your play to avoid alerting your opponent. If you always play the same element, they will figure it out, and that will turn into a bias. And finally, as an aside, this thought process of finding an edge, doing win or doing more and doing less is actually identical to counting in a casino. With a optimum play in 21, a player can develop a somewhat more than 0.5% advantage, somewhere between 0.5% and 1% advantage. So our pseudocode for this process was setting up the probability for each choice. We've seen how that was done in the previous inputs. Your opponent picks a choice at random, but has a bias. You make a choice according to your table of probabilities. On a win, you increase your future probability. On a loss, you decrease your future probability. Those probabilities are given here. B rock is Betty's probability of playing a rock. B paper is Betty's probability of playing paper. And B scissors is Betty's probability of playing scissors. And when we set up Betty, we take the number 333 and put it into all 3 probabilities. So this is based on a probability average or probability table up to 1,000. And the plays will be as some ratio to 1,000. So how's Alan play goes, we generate a random number. If that number is greater than 500, Alan plays rock. If it's greater than 250, he plays paper, and otherwise he plays scissors. And those specifications are down below. The random here is taken from Win32 fourth, has apparently a very good random number generator in it. And they actually seed it by getting a random keystroke when you initialize the game. When you log on, or when you log on to Win32 fourth, one of the setup processes is to initialize the seed for the random number generator. So there is Alan's strategy. Betty's choice says she chooses a random number of 0 to 999. If it's greater than the probability of scissors and paper, then she plays rock. If it's greater than the probability of scissors, then she plays paper. Otherwise, she plays scissors. I'll go through that again. We add together the probability of paper and scissors. What remains is rock. So she would play rock. Otherwise, if it's greater than scissors, she plays scissors. And finally, the default choice is playing scissors. And we see her code down below. There's Betty's strategy play. So Betty's adjustments. In this case, I chose to adjust her play by 0.5% of her current probability. So this is the first time I've actually used linked case statements. First, for Betty's update, we figure out what her last play was. Betty's last play is either gives us a 0 for rock. If her last play was paper, it was a 1. And for her last play with scissors, it's a 2. That gets fed into the case statement down below, and this selects the probabilities. 0 is a tie. 1, 3, and 5 are losses, and so she does a reduction. 2, 4, 2, 3, and 6. She's a win. So we're doing a ratio to 1,000, where you see the 995. This will reduce the probability by 0.5%. Where you see 1005, this will increase the probability by 0.5%. Down on the bottom line, there's 1,000 */swap. That does the ratio adjustments and applies the value into her future probability table. So here's the result. I will mention as an aside, in running this 100,000 games, the time is 0.4 of 1 second. To run 1,000,000 games is 4 seconds. I was astonished at the speed of Win32 and a modern computer. In the past, we had a lot of concerns on Forth about minimum code size and optimizing code for speed, but with 400 megabytes to play with and 2 gigahertz processor speed, those concerns kind of fall away. So at match 1 at the top, Alan has a 100, so 100% of Alan's games at match 1, he won. And by match 100, we see there were 31 ties. Alan won 33 times and Betty won 36 times. So she's now has a lead over Alan by 3 games. And over on the extreme right on the second row, you see that she plays scissors now 31 times, 31% of the time, and plays paper 36% of the time. So her strategy has developed the fact that scissors works against her and paper works for her. At match 500, third row, by the letter A, you see that now she only plays scissors 19% of the time, and she plays paper 45% of the time. And again, these changes are made incrementally slowly and at random to avoid giving the clue to your opponent what you're doing. Down around match 1,500 at the letter B, you see that scissors have declined down to 0. She no longer plays scissors. And now to improve the game, she switched over to playing rock less often. Now, oddly, the letter 20, the number 28 by B shows that her percentage of playing rock has actually increased, which is anti her strategy. But this is effect due to random play and the fact that over short periods of time, you can have deviations from the trend. So by the next to the last row, matched 1,600, she's now dropped down to playing rock only 5% of the time. She's not playing scissors at all. On the last end at 1,700, she no longer plays rock or scissors or rock, plays paper 100% of the time. And at C, we see the long-term results. Again, the number of ties at 30 is about what we expect. About 1/3 of the tie games, even at fully random, we're going to get ties. Alan's wins have dropped to 28. Betty's have gone to 41. And as an aside, this illustrates the law of large numbers, deviations over the short term, but inexorably, when you have an advantage, if you play it consistently, you will come out. And this is why the casinos in Las Vegas have billion-dollar showrooms and hundreds of $1 million of lights up and down the strip. So in conclusion, I found the gameplay was remarkably simple. I did it from a couple of case statements in a table. I actually wrote this about 3 times and homed in on those at the end. At the beginning, I was actually using more, fourth decision written if then else structures, homed in on the tables as a clean way to do it. I found out user input and scoring was simple, where I gave the rock, paper, and scissors numbers and let the players input them by name and let the numbers take over. And finally, we see that even against a very gross player, where Alan is playing rock half the time, it still takes many matches to slowly develop a strategy that's effective. And again, as I just mentioned a moment ago, this all is why casinos stay in business, a small edge over a large number of plays. Do we have any questions? We're speechless. Thank you very much. I found this at the beginning. I thought this was going to be more challenging than it turned out. Like so much of fourth, once you get into it, you start to think about the problem and the code almost writes itself. I mean, the code one step at a time, you lay out what you want to achieve, and then the code just seems to blossom. So I'll turn back to Kevin and to Dave. Thanks so much for your kind attention.
Sometimes the space bar works to unmute me. Sometimes it doesn't. It just goes to show you. And Charles Curley pointed out Zoom is acting up because it wasn't written in fourth. Although I've seen some pretty flaky fourth code. It's easy to write flaky fourth code. It's hard to write code that works, period. All right. On that cheerful note, I'd like to announce that we're going to rearrange the schedule a little bit. We're going to push Brad's talk about WebSent